Before going further, I want to talk about date dimension. Date dimension is a dimension table based on date, which contains all possible details on date. And typically, it is built in advance for anywhere between 5 to 15 years, not more than that. And it contains all the column that you can think of for date. For example, definitely it would have date key, then date, day of week, day of month, day of year, and other types of days also like fiscal month, fiscal year, etc. Then it contains information about weeks, months, last day, week ending date, fiscal week, and a lot more. So the reason I'm covering date dimension separately, because in almost all the data modeling that you do for data warehouse, you'll have to create or you'll have to use date dimension. And for all the cases, method of creating date dimension table is similar. So if you already have a date dimension table in your environment, maybe for a different data mart or a different data warehouse, you can use that in your data warehouse also. Now, having talked about fact tables, dimension tables, and grains, let's discuss the dimensional modeling steps. The first thing, just a small recap. Fact table contains the facts of a business process. So facts meaning that whatever your business is indulged in. So let's say if you take example of a retail business, then the business would be selling individual products or individual items to customers. If you are talking about vehicle dealership, then business would be selling car accessories or individual cars. So those should be kept in the fact tables. And then we have dimension tables, and dimension tables contain the textual description or non-textual description of the business entities. Then we have grains. Grains is basically the lowest level of granularity at which your business runs. So the data that runs your business, and we capture that at the lowest level of granularity. Now, these are the three main components of dimensional modeling. Now, based on these, here's the step for the modeling. The first one is understand the business process, which is pretty obvious because you'll have to understand the requirement of your business. And if you see the dimensional modeling, if you see the fact tables, it represents the records based on the reports that you want to run. So in the previous exercise, I asked you to define the grains. Now, the definition of grain would depend on the business statement. You cannot define grain abruptly. It has to follow a certain business pattern. So that's what the business process is. Then definitely you'll have to define the grain followed by dimension tables and fact tables. Let's take an example, and I'll take example of the retail store wherein I have customer table, orders, order items, products, and seller tables. Now, why am I taking these tables? Because I have provided sample data for these, and you can actually use this dimensional modeling technique to create a data warehousing using the sample data that I have provided. So, how the ER diagram would be? Obviously, we are talking about dimensional modeling or data warehousing, but before that, let's see how the entity relationship diagram would be, because that would be the OLTP data modeling technique, right? So we have these tables, we have customers, and these are the columns, then orders, order items, products, and then sellers. So the ER diagram would be the collective entity relationship diagram. What are the entities? Entities are customers, orders, order items, products, and sellers. These are the entities. And then we'll have to define the relationship. So what is a relationship? Relationship is based on data. Now first, let's talk about the relationship between customers and orders. So for that, the process is very simple. Let's get inside customer's entity and take a perspective from customers. So let's see for one record. For one customer record, how many order records can be there? Of course, a single customer can order many a times. So there can be multiple orders for each customer. So this is how the relationship would be at one end. Now let's get inside the orders entity. For each order, how many customers can be there? There can be only one customer per order. So this is how the relationship would be. So between customers and orders, it is one-to-many relationship, and between orders and customers, it is many-to-one relationship. What about orders and order items? For each order, there can be multiple order items because a single order can contain multiple items. So this is how the relationship would be. Now what about order items? For each order item, there can be only one order. The same item cannot be there in multiple orders. So the relationship would be like this. So between orders and order items, it is one to many, and order items and orders, it is many to one. Now between order items and products, for each order item, there would be only one product because you cannot have multiple products in a single item. Now what about products? So if you go to products, for each product, there can be multiple items because the same product ID can be there in different orders. So the relationship would be one to many. Then finally, we have to define the relationship between orders and sellers. For each order, there would be only one seller. There cannot be more than one seller for a single order as per the data that I have provided. Of course, I mean the seller would make sense for individual order items, but the data that I have provided is like this. For each order, there would be only one seller, and for each seller, there can be multiple orders. So the relationship would be like this. So this is the easiest way to define the relationship. Go into one of the entities and see how many records would be there in the other table for one record of this table. Do the same in the other entity also, and then it would be pretty clear. Now after defining the OLTP data model, you have to define the data model for data warehousing. But we cannot define it abruptly. We need to have requirements. So let's say these are the requirements. We have inventory management, and it says that based on the product sold across region, meaning across zip code, across city and across state, inventory should be planned for each seller based on the products sold. Remember that. Then customer offer is another requirement. So there would be reports created based on the most used payment method. EMI options would be given along with cashback offer to each customer or to different customers. Now again, I mean, how do you find out the most used payment method? The amount of items or amount of products sold for each type of credit card or each type of payment method. Then we have seller offer based on the product sold and rating of sellers. They will be given discount on raw products. This is mainly to increase the adoption of B2B or increase the selling or reward the sellers. Then there's one more wherein the business analysts want to find out the trend of selling. In this, we have to find out the trend of product sales over the months in a year. Again, product sold over the months in a year, and it will be used in manufacture plans for planning, maybe streamlining the supply chain or assembly line, etc. So now let's take these requirements one by one. First, we'll have to define the grain. These are the business processes that I have shown you. Now, what about the inventory management? What would be the grain? So it says based on the products sold across the region. Now, these are the tables that we have. And how do we find the product sold? So we'll have to sum up across all the products, right? And basically order items, because if you see here, we have order ID, product ID, and then we have price for individual products in the products table, and based on products sold across region. So for that, we'll have to take the city, zip code and state from customers table. So we'll have to sum up based on individual items sold. So to find this out, we'll have to know the products, individual products sold. So the grain would be individual products or items. So that's what the grain for this requirement. So let's go to the next one, which is customer offer. And we have these records. So based on the most used method. So how do you find out the most used payment method? Either you use a count on order ID, or you find out the price, total price for each payment method. If you are using count, then I think the grain should be at order level. So only order would do. We do not need anything else. Order ID followed by the count. But if you have to find out based on the total amount, then you would need the individual item also. So as you have already defined a grain which is at lower level than that of order ID, so it's better to use that grain, because remember that if you already have a lower level grain and you have another business requirement which needs a higher level grain, you do not have to define two fact tables unless absolutely necessary. So in this case, I'll keep the grain similar. So it will be products and order items. Okay, so now I'll have to define the dimension tables. So we have date dimension, which would be like this. This would anyway be needed, and it would be needed here also because we have order date, we have delivery date, etc. Then we have customer, which would contain all the customer information, customer ID being the primary key. Then we have seller, which would contain all the seller information, seller ID being the primary key. Then we have product. So in product dimension, we have product ID and product name, maybe product description also. And then payment. This is a new table wherein we'll have a payment ID and payment method. Now, if you notice one thing, all the tables end with underscore DIM. And this is actually a regular practice that the dimension table should be named that ends with underscore DIM. So these are the various dimension tables. What about the fact table? So the fact table would be order with individual products as line items. So definitely order ID would be the primary key, but order ID would not be unique because each order would have multiple product IDs or multiple item IDs. So we'll be using product ID also as the primary key. Now the combination of order ID and product ID would be unique, and this can be thought of as a grain because these two are unique and these two are or define the business process, which can be captured in a quantifiable manner like price and discount. So we can add price and discount also. So this is how the fact table would be, and as you can see, the name ends with underscore fact, just like underscore DIM. So we have order ID and product ID as primary key. Then we need to have customer ID, seller ID, date key, and payment ID, so that we actually can get information or do summation or aggregation across all these dimensions. And then we have price and discount. Dimension tables. Let's draw the star schema. So we have the orders table, orders underscore fact, and then you have multiple dimension tables. So let's look at the relationship between the fact table and all the other dimension tables. Let's get into customer underscore dim. For each customer, there can be multiple products. So this is how the relationship would be. But for each product, there would be only one customer. When I say each product pertaining to one order, right? So now if I think about it, for each order, there would be only one customer. So this is how the relationship would be. Let's look at orders, fact, and seller. For each seller, there would be multiple products and multiple orders. But for each order, there would be only one seller as per our data. Each product would have multiple items, which is the combination of order ID and product ID. But for each product, there would be only one product ID in the order. Similarly, the relationship would be same for payment dimension and date dimension also. So this is how the star schema would look like for the example that I have mentioned. So take a pause here and try to understand this, how I started from the data or I started from the ER diagram and then landed in this star schema using the dimensional modeling technique.